Hello Ace, this is RetroTK2 and today we're talking about generics in C#. If this is your first video in the C# series, I'd strongly suggest watching it from the start. Card is on your screen now. And if you haven't already, might I suggest downloading the channel files that accompany this video. Card should be on your screen once again. So let's get started. What are generics? Well, according to the Microsoft docs, generics introduce the .NET framework to the concept of type parameters, which make it possible to design classes and methods that differ the specification of one or more types until the class or method is declared and instantiated by client code. For example, by using a generic type parameter T, you can write a single class that other client code can use without incurring the cost or risk of runtime casts or boxing operations. We'll go into casts a little bit later in this series, Ace, and I don't think we'll ever really touch upon boxing operations, although maybe we could later on down the line. Generics overview. Use generic types to maximize code's reuse, type safety, and performance. The most common use of generics is to create collection classes. The .NET Framework class library contains several new generic collection classes in the system.collection generic namespace. These should be used whenever possible instead of classes such as ArrayList in the System Collections namespace. You can create your own generic interfaces, class, methods, events, and delegates. Generic classes may be constrained to enable access to methods on particular data types. Information on the types that are used in a generic data type may be obtained at runtime by using reflection. Again, yes, we will touch upon reflection maybe a lot later. I don't even think we'll touch upon it in this series, but hey, it is what it is. Okay, so an introduction to generics. Generic classes and methods combine reusability, type safety, and efficiency in a way that their non-generic counterparts cannot. Generics are most frequently used with collections and the methods that operate on them. Version 2.0 of the .NET Framework class library provides the new namespace System Collection Generic, which contains several non-generic based collection classes. Of course, you can also create custom generic types and methods to provide your own generalized solutions and design patterns that are type safe and efficient. The following code example shows the simple generic linked list class for demonstration purposes. I'm not going to go over the actual linked list here, because I'm going to give you my own example of it. Benefits of generics. Generics provide the solution to a limitation in earlier versions of the Common Language Runtime and the C# language in which generalization is accomplished by casting types to and from the universal base type object. By creating a generic class, you can create a collection that is type safe at compile time. The limitations of using non-generic collection classes can be demonstrated by writing a short program that uses the ArrayList collection class from the .NET class library. An instance of the ArrayList class can store any reference or value type. And there is the actual example that they give you. But this convenience comes at a cost. Any reference or value type that is added to an ArrayList is implicitly upcast to object. If the items are value types, they must be boxed when they are added to the list and unboxed when they are retrieved. Both the casting and the boxing and unboxing operations decrease performance. The effect of boxing and unboxing can be very significant in scenarios where you must iterate over large collections. The other limitation is lack of compile time type checking. Because an array list casts everything to object, there is no way at compile time to prevent client code from doing something such as this. And then here is they try to cast what seems to be just a normal standard reference object to an int. And there's no way to actually ensure that the object that you add to the list is going to be of type int. This is the problem that generics tries to solve. Although perfectly acceptable and sometimes intentional, if you are creating a hereditarist collection, combining strings and ints in a single array list is more likely to be a programming error, and this error will not be detected until runtime. In versions 1.1 and 1.0 of the C# language, you could avoid the dangers of generalized code in the .NET Framework base class library collection classes only by writing your own type-specific collections. Of course, because such a class is not reusable for more than one data type, you lose the benefits of generalization, and you have to rewrite the class for each type that will be stored. What array lists or other similar classes really need is a way for client code to specify on a pre-instance basis the particular data type that they intend to use. That would eliminate the need for the upcast to object and would also make it possible for the compiler to do type checking. In other words, array lists need a type parameter. That is exactly what generics provides. The docs then go on to give an example of the list generics case, which we've used before, but we haven't went into as much detail as I would like, but we will certainly in this video. Generic type parameters. In a generic type or method definition, a type parameter is a placeholder for a specific type that a client specifies when they instantiate a variable of the generic type. A generic class, such as generic list T listed in Introduction to Generics, cannot be used as is because it is not really a type. It is more like a blueprint for a type. To use generics T, client code must declare and instantiate a constructed type by specifying a type argument inside the angle brackets. The type argument for this particular class can be any type recognized by the compiler. Any number of constructed type instances can be created, each one using a different type argument as follows. And as you can see, yes, lists can have float, example class, example structs. You can have a different list for all different types, which makes it unbelievably useful. In each of these instances of generic list, every occurrence of T in the class will be substituted at runtime with the type argument. By means of the substitution, we have created 3 separate type-safe and efficient objects using a single class definition. You can see how unbelievably useful this stuff is, yes. Well, hopefully you can. Type parameter naming guidelines. Do name generic type parameters with descriptive names unless a single letter name is completely self-explanatory and a descriptive name would not add any value, like so is. Consider using T as a type parameter name for types with only single letter type parameters, like so is. Do prefix descriptive type parameter names with T, like so is. Consider indicating constraints placed on a type parameter in the name of parameter. For example, a parameter constrained to iSession may be called tSession. Fairly self-explanatory there, yes, hopefully for you. Okay, let's have a little look at constraints on type parameters. Constraints inform the compiler about the capabilities a type argument must have. Without any constraints, the type argument can be any type. The compiler can only assume the members of object, which is the ultimate base class for any .NET type. If client code tries to instantiate your class by using a type that is not allowed by a constraint, the result is a compile time error. Constraints are specified by using the where contextual keyword. The following table lists the 7 types constrained. Where T is a struct, type argument must be a value type. Any value type except nullable can be specified. For more information, see using nullable types. We've already seen nullable types, of course, in a previous video. Where T is a class, the type argument must be a reference type. This constraint applies also to any class, interface, delegate, or array type. Where T is unmanaged, the type argument must not be a reference type and must not contain any reference type members at any level of nesting. Where T is a new, the type argument must have a public parameter list constructor. When used together with other constraints, the new constraint must be specified last. Where T is the base class name, the type argument must be or derive from the specified base class. Where T is the interface name, the type argument must be or implement the specified interface. Multiple interface constraints can be specified. The constraining interface can also be generic. Where T is U, the type argument specified for T must be or derive from the argument supplied for U. Hopefully that all makes sense to you. Some of the constraints are mutually exclusive. All value types must have an accessible parameter list constructor. The struct constraints implies the new constraint, and the new constraint cannot be combined with the struct constraint. The unmanaged constraint implies the struct constraint. The unmanaged constraint cannot be combined with either the struct or new constraints. Again, yes, we haven't went over structs yet, but we will certainly later on in the series. Why use constraints? By constraining the type parameter, you increase the number of allowable operations and method calls to those supported by the constraining type and all types in its inheritance hierarchy. When you design generic classes or methods, if you will be performing any operations on the generic members beyond simple assignment or calling any methods not supported by system.object, which is essentially pretty much every class is, you will have to apply constraints to the type parameter. For example, the base class constraint tells the compiler that only objects of this type or derived from this type will be used as type arguments. Once the compiler has this guarantee, it can allow members of that type to be called in the generic class. It then goes on to give a nice example of the generic class list. By all means, feel free to check that out. And it, of course, has the type constraint employee. So T would have to equal or have to derive from employee or be an employee class as well. Constraining multiple parameters. You can apply constraints to multiple parameters and multiple constraints to a single parameter, as shown in the following example, like so is. Unbound type parameters. Type parameters have no constraints, such as T in public class sample class, are called unbound type parameters. Unbound type parameters have the following rules. The not equal to and equal to operations cannot be used because there is no guarantee that the concrete type argument will support these operators. They can be converted to and from system.object or explicitly converted to any interface type. You can compare them to null. If an unbound parameter is compared to null, the comparison will always return false if the type argument is a value type. Type parameters as constraints. The use of a generic type parameter as a constraint is useful when a member function with its own type parameter has to constrain that parameter to the type parameter of the containing type, as seen in this following example is. In the previous example, T is a type constraint in the context of the add method and an unbound type parameter in the context of the list class. The usefulness of type parameters as constraints with generic classes is limited because the compiler can assume nothing about the type parameter except that it derives from system.object, which is the same as pretty much any object in C# is. Use type parameters as constraints on generic classes in scenarios in which you want to enforce an inheritance relationship between two type parameters. Okay, so an absolute bucket load of information there is, so let's have a little look at some of this in our code. Open up Unity and create a basic C# script. As always, make sure you give your script a different name than any other class in your project. I'll also be using Unity Spice for all our logouts here, Ace. If you'd like to get it yourself, follow the card on your screen now, and then follow the instructions after that. Right, so generics, Ace. Probably the most common generic type that you'll ever use is the list type, Ace, and you can put in anything you want here. You could even just put in a standard object, but we will put in ints for this sake of argument, and then you can create it like so. New list int. And there we go. Yeah, you can also add to this list and use it like a standard array. I don't necessarily want to go too much into this one, Ace, because I want to show you the list in the next video. So with this one, we've already seen that you can use generics with the action type. If you remember from the action and funcs video, you can see, you'll remember that we could put in different generic types for the different parameters representing the signature of the method. So if I put in a string parameter here, and we call this one action, then we could go and add in use a delegate that would have the type x as the integer, and we could add 1 to the x if we wanted to, for whatever reason. Again, pretty standard is. So yeah, you can use these, and of course, as we know, you could add in a int type here if you wanted to. Actually, you can't actually add to that. Oh, well, I suppose you can, but let's just add this. Bit stupid is, but hey, we'll go for it. And then we will have this action 2, and then we will add to that one. So that makes a wee bit more sense. So really the benefit here is that you don't have to have an action string class like so, and then a subsequent action int class. You can of course just have the one action class that does all the stuff under the hood and treats these just as it would any other type. I believe there's probably some constraints on this, although I don't think there is. Yeah, so as you can see, there's no constraints on the action generic class because you can pass in object. and it will happily go for it. But as you can see, we get a little bit of errors here, since of course you can't do an addition to the object type. Okay, so let's go and create a class that takes a generic parameter, and we will call this generic class, and we will add in our parameter, or a type, sorry, of t, like so. And then we can also put in our constraints, so where t is a class and also has the new default parameter constructor, parameterless constructor is. And that's excellent. Okay, so now we can do stuff with our t if we want to. Let's just generically log the thing, since it seems like a good idea to do. So let's go void, just a standard log. And here we're going to just use t like so, where we would pass in the actual object we want to use. Call it my obj, and then do my obj.toString.log. Nothing too crazy there is. Could have probably got away with this even being unbound, I guess, if you wanted it to be. And now if I go and create my very own GC, we'll say, and call this new generic class. Come on, there it is. And we will pass in a type string. Why not? Oh, I get it. Okay, because string is not a class, string must have a public. Okay, so it doesn't have a public parameterless constructor, of course. Incidentally, if I went and took this away, then it would work. Kind of makes sense, I suppose, that it doesn't have a parameterless constructor. So let's create our own class then. We will call this my class 35, I guess. And we will, of course, create it with its, I think it will have its own parameterless constructor anyway. The only time it doesn't get, yeah, of course, the only time it doesn't get its own parameterless constructor is if we go and explicitly create something like so. Then it's going to complain because it doesn't have a parameterless constructor. But we can, of course, bypass that is by putting in something like this. Sorry, something like that. Excellent. Something like that. That's perfect. Yes. You can also add a constructor to your generic class if you want to, like this. I actually don't even think you need the t here. Yeah, it's going to complain because of that. And then we can pass in the my object like so. And then now we can create a reference to the, or create a field, sorry, that is assigned to the my object. And now it will log it out like that. And now I want to add in the my class. So let's go and create a new my class, come on, 35, like so. And let's do gc.log. gc.log isn't working for some reason. I tell you what, is my computer is being unbelievably slow for whatever reason. It is just not handling it today. It could be the heat. Okay, so now let's go and attach this to any game object after this compiles. Attach this to any game object in your scene and run your game. And there you go, you get my class 35 out here. Very standard stuff, unbelievably useful. With the constraint stuff, it's pretty useful too, yes. And of course, I'll just show, for the sake of argument, that you can create an interface. int 35, I guess, and you can of course have your own type parameters here, like that. Parameters coming like craziest. And you can also put in multiple t's if you want to. But as they've said, it's probably best to actually give these some sort of name, such as this, I guess, input, output. Where this becomes brilliantly useful is actually whenever you're using stuff like save files and things like that, where you can actually, you know, because saving and loading or whatever operations are very, very similar for different types of objects. But then you can just pass in the actual object to be serialized, and it will just save it out and load it in accordingly. And you can have it for multiple objects, which is really cool, I must admit. Because again, it saves you having to go and create those other different classes, like, you know, I guess save int and then load int and I don't know, or whatever, persist, I guess. Persist is probably persistent, and then having load and save, and then having to inherit from other things and whatever. Just have persist and then put in the actual generics like so. makes it so much better. And I can't really think of anything else to say about generic Ace. I think the docs covered it pretty well. The constraints are awesome. The parameters are awesome. You can actually return, if you want to, of type T, which is pretty cool. Get object, I guess, we'll just probably pass in. Should you want to do something like this, and it will actually, instead of you having to get out the actual, rather than having to cast to the object, I'll just type in lol here, why not, and GC, it will actually be of the correct type. I, of course, haven't made that public, which is the problem there, and get object, like so. And then lol will be of type myClass35. Which is pretty useful, this, as opposed to having to do this and then having to actually, this being of type object and having to actually cast this thing, such as this, myClass35, which is the reason why generics was, of course, invented is. We'll get on to casting, of course, a little bit later in the series, not that far away, actually, probably, 1 or 2 episodes, and then we will be on to that Ace. And I think that'll do. I don't really want to overload too much. Okay, well, I suppose I'll show you as well that you can have inheritance going on here as well of this, and we will type in TT. So as you can see, you can have it inheriting the interface, T input, T output, and also having it so that it's the same type as T. I think you can also actually have U and V here if you wanted to. No, because of course you would have to pass in U and V to your type like that, which makes sense is. And then U and V would be used in the N33, and you can of course add in those constraints for the actual parameters themselves as well is if you want to, something like this. Oh, string of course can't be, oh, why can't string be used? Oh, fair enough, okay, I guess you can't use string, I will just use class anyway. And then of course you can also have another where for the V, and maybe just something like myClass35. Yeah, that'll do perfectly, yes. So yeah, happy enough, Ace. And of course we're getting errors now because this is crying about all this stuff. We'll not worry too much about that, and we will type in T, leave that as a comment, and that'll do, yes. So yeah, rate, comment, and subscribe, yes. I hope you're enjoying this series. I am loving the progress that we're making with it. I am neglecting other series, I know, so hopefully I'll be able to pick them up as well. You can email me at retrotk2@gmail.com if you're having any problems with generics. Thank you for watching this, and I'll see you in the next video.